We live in a world that thinks, not in the way we do, with emotion or intuition, but with speed, precision, and infinite memory. Today, the computer is invisible. It is in our pockets, our walls, our cars, and even our minds. But it wasn't always this way. Before electricity lit up the dark, computation was physical. It was heavy. This is the story of how we taught stone and metal to dream. From the clacking gears of the 19th century to the silent hum of artificial intelligence in 2026, this is the evolution of a machine. London, 1837. Charles Babbage, a mathematician with a mind too big for his time, sketches a monster. He calls it the Analytical Engine. It is not electronic. It has no wires. It is a cathedral of brass cogs and levers, designed to be powered by steam. Babbage saw a calculator, but a young woman named Ada Lovelace saw something else. While translating notes on the engine, she wrote an algorithm, the first in history. But more importantly, she had a vision. She realized that if numbers could represent letters, or musical notes, the machine could compose symphonies. She saw the soul in the silicon before silicon even existed. For a century, however, her dream remained trapped in ink and paper. Electricity replaces gears. The room-sized brain awakens. Fast forward to 1945. The world is rebuilding after war. In a room at the University of Pennsylvania, a beast wakes up. The ENIAC. 30 tons of steel, 18,000 vacuum tubes. It consumed enough electricity to dim the lights of Philadelphia. It didn't think in words. It thought in pulses. On, off, 1, 0, binary. At its core, every complex video game, every AI model, every message you've ever sent, is just billions of these tiny switches flipping in the dark. But vacuum tubes were fragile. They burned out like light bulbs. Then, in 1947, Bell Labs invented the transistor, a tiny switch, no heat, no bulk. This small invention triggered Moore's law, the observation that computing power would double every 2 years. It was the beginning of the shrink. The room-sized brain began to fit on a desk. And then, in 1957, came FORTRAN. For the first time, scientists didn't have to speak in the machine's native tongue of ones and zeros. They could write in English-like syntax. It was the first high-level programming language. The barrier between human thought and machine execution had just been breached. Computers leave the lab and enter the home. The world begins to speak a common digital language. By the 1960s, computers were powerful, but hostile. You had to speak complex code to use them. Then, Douglas Engelbart invented the mouse. Suddenly, you didn't have to command a machine, you could point at it, you could touch it. In 1972, at Bell Labs, Dennis Ritchie forged a tool that would become the bedrock of modern computing, the C language. Before C, programmers were either writing impossibly complex machine code or using high-level languages that couldn't talk directly to hardware. C was the perfect bridge. It gave developers low-level access to memory and processors, but with a readable, structured syntax. This power made it the ideal choice for building operating systems. Unix was rewritten in C, and soon after, Windows followed. To this day, C remains the foundation upon which our digital world is built. Every time you boot a computer, use a smartphone, or connect to the internet, you are relying on code written in, or inspired by, C. It is the silent, enduring engine of technology. But the real revolution wasn't in the lab. It was in the garage. 1976. Steve Wozniak and Steve Jobs. They were building for you. The Apple I represented a shift in power. Computing was no longer a utility for the elite. It was a tool for the creator. But these personal computers were islands. They couldn't talk to each other. The solution was packet switching. Instead of sending data in one solid block, the internet broke messages into tiny pieces, sending them along different paths, reassembling them at the destination. It was resilient. It was decentralized. In 1989, at CERN, Tim Berners-Lee invented the World Wide Web. He didn't patent it. He gave it away. Overnight, the Library of Alexandria was rebuilt, accessible to anyone with a connection. The world shrank. In 1991, Guido van Rossum released Python with a radical idea. Code should be as easy to read as plain English. While other languages obsessed with complex syntax and curly braces, Python used indentation and clean lines to prioritize human understanding over machine complexity. For years, it was seen as a simple scripting tool for automation. As the world began drowning in data in the early 2000s, Python's vast library ecosystem made it the natural choice for analysis. Then came the AI revolution. From training neural networks to analyzing climate models, Python proved that simplicity isn't a limitation, it's the ultimate superpower for innovation. Also in 1995, James Gosling introduced Java with a revolutionary promise: write once, run anywhere. In an era where software had to be rewritten for every different computer and operating system, Java solved the fragmentation problem. It ran inside a virtual machine, meaning the same code could work seamlessly on a Windows PC, a Mac, or a server. This portability made Java the backbone of enterprise computing. Banks, governments, and massive corporations built their critical infrastructure on it, but its reach extended far beyond servers. When mobile phones evolved into smartphones, Java became the native language of Android. It taught the world that software shouldn't be trapped by hardware, and that reliability and scale matter more than raw speed. Also in 1995, Brendan Eich created JavaScript in just 10 days. Originally designed as a lightweight scripting language to add simple interactivity to static web pages, no one predicted it would become the most important programming language. As the web evolved from digital brochures to dynamic applications, JavaScript evolved with it. It moved from the browser to the server with Node.js, enabling full-stack development in a single language. Today, every website you visit, every web app you use, and even many desktop and mobile applications rely on JavaScript. It powers the interactive layer of the entire internet. What started as a quick hack to make buttons click has become the universal language of the web, proving that sometimes the most impactful tools are born from necessity, not grand design. Hardware becomes invisible, software becomes intelligent. The computer is no longer a device, but a utility. How does a modern computer actually work? It's a layered cake of abstraction. At the bottom, the raw, physical hardware. In the middle, the operating system, translating human commands. And at the top, the applications. We no longer interact with a metal, we interact with the layers above it. We stopped buying servers and started renting them. Amazon, Microsoft, Google. The cloud meant that your data wasn't on your device, it was everywhere. Startups could launch globally in seconds. The barrier to entry collapsed. By 2014, programming had changed dramatically. Developers no longer wanted to manually manage memory. Apple recognized this shift and introduced Swift, a language designed for safety, speed, and developer joy. Swift replaced Objective-C with modern features like optional types, closures, and protocol-oriented programming, all while maintaining blistering performance. But Swift wasn't alone. Across the industry, languages like Rust, Kotlin, and Go embraced the same philosophy: empower developers to write safer, cleaner code faster. These modern languages abstract away the dangerous complexities of the past, letting programmers focus on solving problems instead of fighting the compiler. They represent a maturity in software engineering, where the goal is no longer just making machines work, but making the act of creation itself more humane, efficient, and accessible. But while the infrastructure became invisible, the intelligence became visible. In 2016, Google's AlphaGo played the world champion of Go. Go is a game of intuition. There are more possible moves in Go than atoms in the universe. A computer shouldn't be able to win, but AlphaGo did. It made move 37, a move no human would ever make. It wasn't just calculating, it was creating. It was the birth of deep learning. Which brings us to now 2026. We have entered the age of generative AI. The machine no longer just retrieves information, it generates it. It writes poetry. It creates images from text. The definition of creativity is being challenged as machines learn to generate. From the clacking brass gears of Babbage's Analytical Engine in 1837 to the silent, invisible neural networks of 2026, we have witnessed the most rapid evolution in human history. We went from machines that could only add numbers, to machines that can write poetry, diagnose diseases, and create art. But as we stand at this incredible milestone, one truth remains constant: technology is only as powerful as the human intent behind it. The code may change, the hardware may shrink, but the dream, to extend the reach of the human mind, remains exactly the same. The history of computing isn't just a story about machines, it's a story about us. And as we look toward the next century, the question is no longer what computers can do for us, but what we will choose to create with them. The timeline continues. And the next chapter is yours to write.